In this lecture, we are going to talk about waves. Waves are closely related to the idea of oscillators. When we looked at oscillators earlier, one of the examples was a mass on the end of a spring. Here we show a mass that is connected to two springs, and each end of the springs are anchored to walls. There is a restoring force on the mass provided by the springs, so it oscillates back and forth around an equilibrium position shown by the dotted line. If we describe this motion in this direction with the variable x, we can draw an axis and have the variable x, and then we can write down a differential equation for this motion. This is equal to the mass times the second derivative of x plus kx equal to 0. And we've solved this before, and the solution is x of t is equal to a times the cosine of omega t, so a sinusoidal oscillation. Now, if we're talking about waves, we're going to connect many oscillators together and then displace one. So here we have a network of oscillators, and we connect them together with springs, so that as we displace one, the disturbance gets transferred down along the chain. So waves are oscillatory displacements or disturbances that propagate in a medium. For example, the network of springs that we saw in the last slide. Other examples of waves are a water dropping into a pool that creates this circular wave spreading out, or sound waves that are coming from a speaker, or light waves that here shown with a prism here, where you have a beam of white light spreading out into the different components of the white light, the rainbow. Even quantum mechanical particles are waves. There are two general types of waves. There are transverse waves, where as the wave propagates, the displacement is in the perpendicular direction or transverse to the motion. Or there are longitudinal waves, where the displacement or disturbance is in the same direction as the motion of the wave. There are two parts then to a wave: propagation and displacement. If we look at a wave and a surfer, the surfer stays on top of the wave and his height never changes as the wave moves him along. If you're looking at a buoy and a similar wave comes along, it lifts the buoy up and then puts it back down in the original place. If we write down a function to describe this wave, or the height of the wave as a function of position and time, then for the surfer, at time equals 0, he's at a certain height. And he remains at that height for all x and for all time, so that x minus vt must be equal to 0. For the buoy, it only goes up at a certain position and a certain time, and for all other times it goes back to its original position. So h is equal to x, the position of the buoy, minus the velocity times time is equal to 0. So at some point, when x minus vt is equal to 0, then the buoy goes up. And that's our introduction to waves.